Every rotation carries within it the seed of stillness. The same conservation of motion that once bound the cosmos together will, over vast epochs, scatter it apart. Stars fade, galaxies drift, and the spirals of creation slowly unwind into darkness. To imagine the universe's future is to follow the trajectory of motion as it lengthens, thins, and finally dissolves. Nothing ends abruptly, it simply loses the ability to turn. The slowing has already begun. Our own planet offers a quiet example. Each century, Earth's day lengthens by roughly 1.5 milliseconds. A minute correction so minute we scarcely notice it, yet one that will, over eons, accumulate. The cause lies in tidal friction. The moon's gravity raises bulges in Earth's oceans that lag slightly behind its rotation, stealing angular momentum and transferring it outward. As a result, lunar distance grows by about 4 centimeters each year. In the far future, Earth and Moon will stand in tidal lock, each showing the same face to the other in perpetual equilibrium. The daily rhythm that defined our history will come to rest. Within the solar system, similar exchanges occur everywhere. Mercury is already captured in a 3-to-2 resonance, 3 rotations for every 2 orbits around the Sun. Venus turns so slowly that its day exceeds its year, rotating backward, likely due to collisions early in its formation. Even planets once vibrant with spin gradually surrender it to the drag of tides, magnetic braking, and internal dissipation. Rotation's energy is finite. Gravity always finds a way to reclaim it. Stars, too, evolve as engines of motion, losing momentum. A young star spins rapidly, stirring its magnetic fields and flinging stellar winds into space. Over time, those winds carry angular momentum away, slowing the star's rotation much as air resistance slows a wheel. Our Sun, now middle-aged at 4.6 billion years, rotates once every 27 days at its equator. When it was new, that period was perhaps half as long. Astronomers call the process magnetic braking. Charged particles escaping the Sun drag its magnetic lines outward, bleeding rotational energy back into the solar wind. This invisible friction is the cost of radiance. Eventually, even gravity's engines exhaust themselves. A star's internal nuclear reactions, balanced for billions of years, consume hydrogen into helium and heavier elements. When that fuel depletes, collapse follows. For stars like our own, the result will be a red giant swelling outward, then a planetary nebula dispersing into interstellar space. What remains is a white dwarf, a dense ember held together by quantum pressure, still rotating but cooling inexorably. For massive stars, collapse is more dramatic. The core compresses into a neutron star or black hole, transforming stored angular momentum into extreme rotational speed. Some neutron stars spin hundreds of times per second, their pulse of radiation marking one of the universe's fastest clocks. Yet even these diminish radiating gravitational waves and particles until they, too, slow almost to stillness. Across the heavens, galaxies replay this pattern at grander scales. When the Milky Way was young, its arms were tight and luminous, new stars igniting in abundance. Now, after more than 10 billion years, its formation rate has fallen drastically. Each generation of stars sequesters heavy elements, reducing the raw material for future creation. Cosmic rotation continues, but the sources of renewal thin. Our galaxy's neighbor, Andromeda, approaches on a collision course that will unite the two systems roughly 4 billion years from now. Their encounter will scatter stars into long tidal streams, while their central black holes spiral together, radiating gravitational waves before merging into one massive, slowly rotating heart. The new remnant, sometimes called Milkdromeda, will settle as a featureless elliptical galaxy, its once majestic spiral arms gone. Rotation remains, but structure fades. Even that structure is temporary. Observations show the universe expanding at an accelerating rate. Galaxies not gravitationally bound to one another recede ever faster, driven by dark energy, the mysterious pressure embedded in space-time itself. As the expansion continues, clusters separate, communication between them ceases, and the cosmos becomes a scatter of isolated islands adrift in night. Each island maintains local motion, stars orbiting, planets turning, but the collective rhythm that once knit them into a cosmic web loosens beyond measure. The fate of that grand unwinding unfolds across timescales almost beyond language. In 100 trillion years, 10 trillion times older than humanity, star formation will have ended throughout the universe. Existing stars will have exhausted their fuel or cooled into white dwarfs. In 1 quadrillion years, gravitational interactions will begin ejecting stars from their galaxies, leaving behind compact cores of remnants, black holes, brown dwarfs, and planetary debris. Galactic rotation will slow, not through friction but through loss, the diffusion of mass outward. The universe becomes quieter, its pageant of motion reduced to stray revolutions in the dark. As entropy advances, even those relics evolve. Over perhaps 100 quintillion years, gravitational encounters will draw the last survivors into central black holes or fling them into the void. These black holes then dominate the cosmic landscape, their rotation a final vestige of the energy once shared by trillions of stars. Yet Hawking radiation ensures even they cannot endure eternally. Through a process predicted in 1974, quantum effects at the event horizon cause black holes to emit faint thermal radiation, losing both mass and angular momentum. The larger the black hole, the slower it evaporates. Still, given enough time, around 100 billion years, even the supermassive giants at galactic centers will fade into particles and photons. Rotation itself will have leaked back into the vacuum from which it came. What remains after this evaporation is difficult to describe. The universe continues to expand, but its contents dilute toward oblivion. Temperatures approach absolute zero. The cosmic microwave background, once 3 kelvins, declines toward nothing. Protons may eventually decay, a possibility suggested by some grand unified theories, leaving behind only leptons and radiation, wandering through immense distances so vast that their wavelengths exceed the curvature of the observable cosmos. With no differences of temperature, pressure, or density, motion loses definition. In that final silence, time as measured by change ceases to have meaning. The cosmos would have reached thermodynamic equilibrium, a state not of sudden death, but of infinite rest, the heat death of the universe. Hey everyone, thanks for stopping by. If you enjoy the content we shared today, don't forget to hit that subscribe button. Yet even this ending contains paradox. Complete stillness may never be realized, for quantum theory insists that the vacuum itself fluctuates. Empty space seethes at infinitesimal scales, particles appearing and vanishing, tiny eddies in the sea of existence. Over inconceivable spans, numbers measured with more zeros than atoms in the stars, these fluctuations could spontaneously create new bursts of order, perhaps a particle, a black hole, or even a new universe. In physics, this is called cosmic renewal, or quantum tunneling, a reminder that absolute stillness cannot hold indefinitely. Motion, the first condition of being, may resurrect even from near nothing. For human minds constrained to brief lifespans, such futures are abstractions. The scales are too large, the epochs too long. But in contemplating them, we glimpse the symmetry that unites creation and conclusion. The universe emerged from motion and will return to equilibrium through the loss of motion. In that regard, birth and death are mirror processes: expansion from compression, rotation from stillness, light from darkness, and back again. The same entropy that erases structure also preserves its memory through transformation. On the way to that distant fate, motion will persist in smaller and more intimate forms. Long after the galaxies dissolve, atomic nuclei may still vibrate, or neutrinos may continue to drift through the cold. Each residual oscillation will be a faint echo of the first spin. Even if cosmological time stretches beyond comprehension, every tick of decay or thaw remains part of the continuum, a whisper that the universe still remembers movement. For humanity, motion's slowing carries philosophical significance rather than threat. Our species will not see the epochs of cooling stars, but understanding them lends perspective. Beneath the urgency of daily time lies the awareness that all motion, even that of our atoms, participates in a single grand cycle. What began with the first rotation will conclude in dispersion. Between those boundaries, consciousness flourishes. The awareness of the universe unwinding is itself a form of reverence, life bearing witness to the mechanism of its origin. Some cosmologists speculate that the story may not end at equilibrium. Theoretical models of a cyclic cosmos suggest that when expansion stretches space-time beyond sustainability, quantum fluctuations could collapse local regions into new beginnings. The contraction or bounce would reverse decay, converting stillness back into motion. Whether or not such rebirths occur, the concept illustrates continuity. Motion, once set in existence, never truly disappears, but changes its scale and form. Even if universes die, rotation remains their inheritance, ready to start the next chronology. Whatever the ultimate outcome, the destiny of movement converges on harmony rather than loss. The unwinding of galaxies is not destruction, but restoration, the return of ordered energy to diffuse potential. In the grand ledger of conservation, nothing vanishes. It transforms from rotation to radiation, from structure to equilibrium. The universe that began as a luminous storm will conclude as serenity, the same energy redistributed into perfect balance. To stand beneath a night sky today is to witness motion mid-sentence. Stars drift slightly between constellations. Galaxies slide silently through expanding space. Our planet turns beneath them with undiminished grace. Every visible point participates in the slow unwinding, yet the pattern remains beautiful precisely because it changes. The awareness that all things move towards stillness gives that movement meaning. When, in some unimaginable future, the last photon fades, it will do so carrying the final remnant of rotation, wavelength stretched across what once was galaxies. That faint ripple will still obey the same equations that governed the first stars, a closing chord echoing the beginning. The universe will not die in catastrophe, but in completion, its energy perfectly balanced, its motion perfectly extended. Perhaps that is the ultimate symmetry. The universe begins with the sound of creation and ends with the sound of silence, both expressions of the same harmony. If a new cosmos is born beyond that silence, it will spin once more, and motion will write again the story that never truly ends.